The entire Earth's crust, from the thin layer of soil beneath your feet to the granite slabs and basalt depths tens of kilometers below, weighs approximately 23 billion tons. All the world's mountains, all the oceanic plates, everything that lies beneath cities, fields, deserts, and glaciers. If you took this entire mass, sifted every cubic millimeter of rock, separated every element from iron and silicon to gold and uranium, and collected together all the residue currently on the planet, you would get no more than a few dozen grams. Just so. Different sources say between 20 and 70 grams. The range depends on the accepted model for the uranium content of the crust. Several tens of grams for the entire planet Earth. How's that for you? The Earth contains about 60,000 tons of gold in its crust. It's rare, but all known reserves would cover the ocean with a layer a nanometer thick. The crust contains about 5,000 tons of platinum. There's approximately 1 GM of radium per 3 million tons of rock, but in absolute terms, it's hundreds of tons. The remainder is a few dozen grams. Friends, welcome to the Fool's Gold channel. I wanted to step away from the well-known metals from the periodic table and focus on an element that few have truly heard of, and for good reason. Today, our hero is the 85th element of the periodic table, astatine, an element that exists on the very edge of physical reality, which no one has ever seen with their own eyes, which doesn't have a single stable isotope, and yet which is currently being used in clinical cancer trials in several countries. If you remind me that we agreed to consider metals first and not deviate from that line, you'd be right. And at the same time, you'd be wrong. Is it a metal? There's no definitive answer. But traditionally, astatine isn't classified as a classic metal. In most chemistry textbooks, it's classified as a non-metal, a halogen, or a metalloid semimetal. However, due to its position in the periodic table, the residue has a unique dual nature. It combines the chemical properties of both nonmetals and metals. What a reversal. Try to find it in the table. Group 17, the lowest line among the stable elements. The halogen group. The word halogen comes from the Greek gals, meaning salt, and genos, meaning begetter. These elements form salts when reacting with metals. The term developed in chemistry in the first half of the 19th century. Sodium and fluoride produce sodium fluoride toothpaste. Chlorine and sodium produce table salt. Bromine and silver produce light-sensitive silver bromide, the basis of an old photograph. Iodine and potassium produce potassium iodide, which is added to table salt to prevent thyroid disease. The residue's neighbors from above are fluorine, chlorine, bromine, and iodine. They all follow a clear pattern. As you move down the group, atomic weight increases, boiling point rises, color darkens, and reactivity decreases. Second, a pale yellow gas. It's the most reactive element on Earth. It corrodes glass and boils at -18 degrees Celsius. Chlorine is a yellow-green gas that boils at -34 degrees Celsius. It was used as a chemical warfare agent in World War I. Bromine is a reddish-brown caustic liquid that boils at 59 degrees Celsius. It's one of two elements that are liquid at room temperature. Dark purple crystals with a characteristic odor boils at 184 degrees Celsius by shuttle. Actually, according to the logic of the periodic table, the remainder should simply be as follows. Even darker, even heavier, even less reactive, but still not a metallogen. In reality, it violates almost all the rules of its group, a sort of anarchist. On the Fool's Gold channel, I try to view information through the prism of personality. So let's start with the man who first described this element 70 years before its creation. In 1869, Dmitry Ivanovich Mendeleev published the first periodic table. His genius wasn't simply that he arranged the elements by atomic weight. Tables of the elements had been compiled before him. John Newlands in England devised the law of octaves, analogous to a musical scale where every eighth element repeats a property of the first. Lothar Meyer in Germany plotted a graph of atomic volume versus atomic weight and saw periodicity. Both were right. Both saw patterns, but neither dared to take the next step. Mendeleev, however, did. He saw in the arrangement of the elements a law of nature powerful enough to predict as yet undiscovered elements, and he wasn't afraid to leave blank spaces, bluntly stating, "Here should be elements we haven't yet found." His colleagues viewed these empty spaces with skepticism. Predicting a non-existent element proved unscientific. Mendeleev persisted. There was a gaping hole at number 85. He named the hypothetical element eco. The prefix eco is the Sanskrit numeral for one, and in his system it denoted something one step below a known element. Mendeleev hypothesized that it would be a dark, heavy substance with a metallic luster, capable of forming volatile compounds similar to iodine, but with more pronounced metallic properties. Jeez. The prediction turned out to be correct in almost every way, with the exception of one circumstance that was impossible to predict in the 10th century. This element cannot be found in the earth in appreciable quantities because it cannot exist long enough to accumulate. The table worked with astonishing accuracy. Gallium was discovered in 1875. The French chemist Paul-Émile Léacourt de Bois-Badran found it by analyzing zinc ore using the spectral method. Mendeleev predicted a density of 5.9 grams per cubic centimeter for eco-aluminium. The actual density of gallium is 5.91. Scandy was discovered in 1879. Swedish chemist Lars Nielsen discovered it in the mineral Exnia. Germany discovered it in 1886. Yeah, we'll get to it soon in a new video. German chemist Clemens Winkler found it in the rare mineral gerolite. In both cases, the properties of the real elements matched the predicted ones. It seemed a matter of technique. Finding the 85th was just a matter of time. Years passed, and the 20th century arrived. Radioactivity was discovered by Baikar and Kurikut, the heroes of our previous video, in 1898. The electron was discovered by Thomson in 1897. The nucleus of the atom was discovered by Rutherford in 1911. The neutron was discovered by James Chadwick in 1932. Physicists were then reshaping the very concept of matter. It was a fascinating time. But the 85th cell of the table stood empty. 30 years, 40 years, 60 years of searching. And then began one of the strangest episodes in the history of science, a series of false discoveries spanned an entire decade. In 1931, American physicist Fred Allison of Alabama Polytechnic Institute announced a discovery. His method was magneto-optical, measuring the rotation of the plane of polarization of light in a magnetic field as it passes through a solution. Each element, according to his theory, rotates its polarization by a precisely defined angle. If a new element is introduced into the mixture, the angle will change. On paper, the method seemed reasonable, but in practice, it was a disaster. The apparatus was insanely sensitive to any external influences. Temperature fluctuations of literally tenths of a degree, mechanical vibrations from a tram passing outside, changes in air humidity, electromagnetic interference in evokes. The device constantly showed signals that didn't exist, artifacts generated by the device itself. Allison and his students didn't notice this because they already knew what they were looking for. They saw flashes on the detector. They interpreted the flashes as evidence. This cognitive distortion is known in science as confirmation bias. The human brain is an amazing pattern-finding tool, and it finds them even where they don't exist. This is why independent replication of results exists in science. Until another group has obtained the same result under different conditions, it's not a given. Olison was studying Brazilian monazite sand, a mineral containing thorium and rare earth elements. He announced that he had discovered the traces of element 85. He named it Alabaman, after his state symbol Ab. Harvard and Berkeley attempted to replicate the experiment. At Harvard, the apparatus showed nothing. At Berkeley, too. An Alabaman disappeared. It was later discovered that Olison had used the same method to claim the discovery of several other non-existent elements. Magneto-optical analysis was deemed unreliable and discarded, but the hunt continued. In 1936, Romanian physicist Horia Holubei and French researcher Yvette Couchois used X-ray spectral analysis, a far more reliable method. They detected weak X-ray lines in minerals that matched those calculated for element 85. They were cautious, double-checked for a long time, and named the element dor. In Romanian, this word means a longing for something somehow unattainable. Quite poetic, don't you think? The lines turned out to be artifacts of X-ray scattering in the measuring apparatus. In 1937, the Indian chemist Rajendra announced the discovery of the element tachyon in Travancore's monocyte. Anomalous spectral lines. Testing revealed that he had mistaken the unusual lines of bismuth under special irradiation conditions for a new element. In 1940, the Swiss chemist Walter Miner announced Helvia while analyzing the decay products of radium. 2 years later, he, in collaboration with the British scientist Alice Lee Smith, announced Anglo-Helvetia. 2 different names, the same non-existent substance. Both works were refuted by the Austrian physicist Bertha Karlik. Bertha Karlik deserves a closer look, as she is a significant figure in our history. Born in 1890 in Vienna, she studied physics at the University of Vienna during an era when academic careers were virtually closed to women. Her scientific home was the Radium Institute in Vienna, one of the few places where the work of female physicists was taken seriously. In 1938, when Nazi Germany annexed Austria, most of the institute's male physicists emigrated, some to Britain, some to the United States, some to Sweden. Gut. Lise Meitner, a physicist who pioneered the discovery of nuclear fission, fled Berlin wearing only a dress and forged documents. Karlik remained. She remained in an occupied country at an institute that had lost half the implicit staff, with reagent supplies disrupted and its international contacts cut off. And she continued to work. In 1943, she and her colleague Bernhard Trudel detected astatite 217 and astatite 219 in the natural decay chains of uranium. Element 85 was discovered in nature for the first time, not synthesized in a laboratory, but found in natural minerals. At the same time, they refuted Minder's helvetium. What he had mistaken for a new element were misinterpreted products of standard radioactive decay. After the war, Bertha Karlik became the first woman to hold a full professorship at the University of Vienna. The first in the history of this university, founded in 1365. Now is the time. Now is the time to ask the long-awaited question. Why were all these researchers wrong? Because they were looking in the wrong places and for the wrong reasons. They relied on simple logic. Since the element is found next to iodine, it must exist in the earth as stable minerals. They were missing the main point. Element 85 does not and cannot have any stable isotopes. Any nucleus with 5 protons is fundamentally unstable. The longest-lived element, astatine 210, lasts 8 hours and 6 minutes. This isn't the time it takes for anything capable of illuminating a spectral line to accumulate in a rock. They were looking for a stable element, but it didn't exist. Having realized this, scientists realized they couldn't find a remnant. They had to create it. The analogy with alchemy is obvious, and for this, a previously non-existent machine was needed. In 1932, physicist Ernest Lawrence of the University of California, Berkeley, created the first working cyclotron. The idea to accelerate charged particles not in a straight line that would have required an accelerator kilometers long, but in an expanding spiral. The particles move between 2 floor-shaped electrodes, called Ds. An alternating electric field accelerates the particles each time they move from one D to the other. A powerful permanent magnet keeps them on a spiral trajectory. Each revolution is a new jolt. By the time the particles reach the edge of the chamber, having described hundreds of spiral turns, they carry enough energy to break through the nuclear barrier of another atom. Lawrence received the Nobel Prize in Physics for this invention in 1939. By the way, friends, maybe we should make a separate video on our Fool's Gold channel about the most interesting discoveries in chemistry and physics that earned the Nobel Prize? Let me know in the comments if you would be interested. But I digress. Back to our story. By 1940, a 60-inch cyclocuapalajan was operating at Berkeley. Weighing approximately 220 tons, it was the largest machine in the world at the time. Emilio Segre also worked in the same lab. Segre was born in 1905 in Tivoli, a small town in Lazio. He studied under Enric at a farm in Rome. He was part of the famous group of boys from Via Ponisperno. A team of young physicists discovered slow neutrons in the 1930s and showed that they caused nuclear reactions with much greater efficiency than fast neutrons. This discovery was part of a direct chain of events that led to the creation of the nuclear reactor. Segre had already discovered technetium, the first synthetic element, together with Carlo Periev in Palermo in 1937 and 1938. Segre was on a business trip to Berkeley when news arrived from Rome. The Mussolini regime had enacted racial laws modeled on Nazi Germany. Jews were being stripped of their government positions. His professorship in Palermo was occupied. There was nowhere to return. Segre remained in the United States, stateless and without a permanent position, with his wife and child on foreign soil. For several years, he worked on temporary contracts, receiving a salary significantly lower than his American colleagues. It was during this period that he, together with Dale Corson and Kenneth Mackenzie, synthesized astatine. The idea of synthesis was simple. Bismuth, the hero of one of our previous issues, element number 83, adds 2 protons to its nucleus. The result is a nucleus with a charge of 85. 2 protons are contained in an alpha particle, the nucleus of a helium atom. 2 protons and 2 neutrons. The bismuth nucleus 209 absorbs the alpha particle and ejects O2 neutrons. The atomic mass is 209 plus 42 equals 201. The charge of the nucleus is 83 plus 2 equals 85. The product is 211. Alpha particles were accelerated in a cyclotron to an energy of 28 mega-electron volts, sufficient to overcome electromagnetic repulsion and enter the bismuth nucleus. In the spring of 1940, a plate of pure bismuth was placed in the cyclotron's vacuum chamber. For several hours, a stream of alpha particles bombarded the target. When the physicists removed the plate and brought detectors to it, the instruments detected bursts of alpha radiation that did not belong to bismuth, polonium, or any other known element. The substance behaved like iodine, was volatile when heated, extractable with organic solvents, but was intensely radioactive. The team conducted a series of chemical tests and published a paper in Physical Review 8 in 1940. Then the war broke out. The cyclotron at Berkeley was redirected to separating uranium isotopes for the Manhattan Project. Astatine's research was shelved. The element was discovered and immediately forgotten. Incidentally, the name astatine comes from the ancient Greek astatos, meaning unstable, shaky. It was officially adopted by UPOC after the war. Prior to this, Alabama, Helvetium, and Doris had competed in various publications. The Greek word which most accurately described the element's key properties, one. But this triumph immediately raised a new question. If uranium-211 residue lives for 7 hours and the longest-lived natural flood for 8 hours, where do those few dozen grams in the Earth's crust come from? The answer to this question takes us deep into the Earth and into the physics of the atomic nucleus. We all know that the Earth is a functioning nuclear reactor. The Earth's crust and mantle contain enormous quantities of uranium-238, uranium-235, and thorium-232. These heavy primordial nuclei have been slowly decaying, without ceasing, since the first day of Earth's existence until today. Each decay releases heat. According to geophysicists' calculations, about half of the heat flow from the Earth's interior is radiogenic in origin. It is this flow that is partly responsible for the mantle remaining hot for billions of years. Tectonic plates move, volcanoes erupt. Kilauea in Hawaii, Etna in Sicily, Fuji in Japan. All of them are fed in part by the heat of decaying uranium. And in these endless decay chains, astatine appears among dozens of Intermediate products. Uranium-238 decays in a 14-step chain to stable lead-200 and 206. Uranium-235 decays in 11 steps to lead-207. Thorium-232 decays in 10 steps to lead-200 and 208. Entire families of intermediate isotopes participate in these chains: radium, rhodon, polonium, bismuth, thallium, and astatine. Astatine-217 is produced in the actinium decay series of uranium-235, uranium. Astatine-219 in the same chain at later stages. Astatine-218 is in the uranium-238 series. Each of these isotopes is an intermediate stopover of seconds. Nature passes them by like a train rushing through a small station without stopping. Natural astatine deposits hold the record for the fastest disappearance rate among all natural elements. Astatine-219 exists for 56 seconds. Astatine-218 is about a second and a half old. And Astatine-250 about a 0 millisecond. Every second in all the uranium ores on Earth, in Kazakhstan, Australia, Canada, Namibia, billions of statin atoms are born and die. Their total mass at any given moment is only a few tens of grams. Like the water level in a sink with a dripping faucet from which the water constantly flows. The level is constant, but the water is new every second. This fundamentally distinguishes statine from any other rare element. Gold is rare, but it has been in the Earth since the formation of the planet. It's rare. Marie Curie processed tons of uranium ore to obtain the first decigram, but it still exists in measurable quantities and lasts for thousands of years. But statine doesn't accumulate in principle. It can't be extracted from ore, can't be enriched, can't be concentrated by mining methods. It exists only as an instant in the decay of another. You know, it's even a little sad to see such short lifespan, like butterflies. Why is 85 protons a fundamentally bad number for nuclear stability? Two forces compete in the nucleus. The strong nuclear force attracts all nucleons, protons, and neutrons to each other with enormous force. It operates only over very short distances, no more than a few femtometers, that is, a few millionths of a nanometer. The electromagnetic force repels protons from each other. They have the same positive charge, and like charges repel each other. It operates over any distance. As long as there are few protons, the nuclear force outweighs the electromagnetic repulsion. But the more protons there are, the stronger the net repulsion, and the harder it is for the nuclear forces to hold the structure together. Neutrons help. They contribute to the nuclear attraction, but they themselves carry no charge and do not repel each other. Therefore, heavy and stable nuclei contain increasingly more neutrons relative to protons. These are so-called magic numbers. I've mentioned them before in previous videos. A special number of protons or neutrons that gives the nucleus additional stability. The concept was introduced by the German-American physicist Maria Goeppert-Mayer in 1949 when she developed the nuclear shell model. For this discovery, she received the Nobel Prize in Physics in 1963, becoming the second woman after Curie to receive this award. Magic numbers: 2, 8, 20, 20, 28, 50, 82, 100, 26. The lead-200 nucleus contains 82 protons and 126 neutrons. Both numbers are magic. This is why lead-208 is the endpoint of several radioactive chains at once. There is nowhere else for it to decay. 85 is not a magic number. It lies between the two magic numbers. A nucleus with protons is unstable with any number of neutrons. It will always strive to reduce its charge through alpha decay, by emitting a helium nucleus, or by electron capture. A stable residue is impossible not because we're not looking hard enough for it. It's impossible because nuclear physics leaves no room for it. After its discovery in 1940, Assel's research was interrupted for almost a decade. Degro was recruited to the Manhattan Project at Los Alamos. There he worked in a group studying the spontaneous fission of plutonium, a critical issue for the design of a plutonium bomb. The problem was this. Initially, the designers considered a cannon design. One piece of plutonium is fired at another, The mass becomes supercritical and an explosion occurs. But Segro discovered that the plutonium-239 produced in reactors contains plutonium-240, which undergoes spontaneous fission at such a high rate that the bomb would begin a chain reaction even before the pieces had time to fuse. A low-power explosion will occur, destroying the charge prematurely. It was this discovery by Segre that led engineers to develop a fundamentally different implosion design. In it, the plutonium charge is surrounded by explosives which simultaneously compress it from all sides, bringing to a supercritical density in a tiny fraction of a second. This was one of the most difficult engineering challenges of the entire project. Astatine waited. Only in the 1950s did chemists return to 1885 and discover that it doesn't fit into the usual framework at all. This key is a sociophobe and an introvert. Look at the halogen series from top to bottom and write down their electronegativity on the Pauling scale. Deuteronomy 3.8, chlorine 3.16, bromine 2.96, iodine 2.66. The trend is obvious. Electronegativity decreases from top to bottom. By this logic, the residue should have an electronegativity of about 22 to 25. Calculations and experiments give around 2.2. This matches the electronegativity of bismuth, a typical metal. For comparison, iron has an electronegativity of 1.83, while copper is a metal by this parameter, but it bil other. By this bilal, but it bilage group. In solutions, the situation is even more interesting. In the presence of strong oxidizing agents, astatite forms positive ions, gations with a charge of 1.1 plus 3 plus 5. This is the behavior of a metal. Metals donate electrons and form cations. Under reducing conditions, astatite can accept an electron as an anion. Astatite is an ion with a charge of -1, like a true halogen. Depending on the chemical environment, it chooses to be a metal or a non-metal. This is why some chemists call astatite a pseudohalogen or a metalloid. It straddles the line between two worlds, and where exactly to draw the line depends on the property being studied. The reason for this duality is relativistic effects in the electron shell. At the center of the astatite atom is a nucleus with a charge of plus 85. Electrons in the orbital closest to the nucleus are forced to move at enormous speeds, approximately 50–60% of the speed of light. According to Einstein's special theory of relativity, an object's mass increases as it approaches the speed of light. The electrons in the inner orbits of the remnant are heavier than predicted by non-relativistic quantum mechanics. Heavy electrons move in more compressed orbits closer to the nucleus. This alters the shielding throughout the rest of the shell. The outer electrons responsible for chemical bonds find themselves in different conditions than those of the lighter halogens. Without taking relativistic effects into account, it is impossible to correctly describe the chemistry of gold, mercury, lead, and thallium. Gold would be silvery, not yellow. The yellowness of gold is a purely relativistic effect. Electron transitions are shifted precisely because of the orbital compression. Mercury would be a solid at room temperature. For astatine, these effects are so strong that they blur the very boundary between metal and non-metal. Several compounds of the astatine have actually been synthesized. Hydrogen astatite is an analog of hydriodic acid. According to calculations and indirect experimental data, it is a weaker acid than hydriodic acid. This again defies the trend. In the series of halogenated acids, strength increases from top to bottom, and hydriodic acid is the strongest. Astatine also defies this trend. Silver astatite is soluble in water, similar to silver iodide. In early experiments, it was deliberately precipitated to concentrate the astatine from the solution. Silver nitrate was added. Astatite precipitated, and the precipitate was collected. This was a simple technique that allowed one to work with trace amounts of a substance. How can one even study the chemistry of a substance containing several million atoms in a test tube? Picogram masses. Physically, there is nothing. A transparent solution, no color, no odor. How can you tell what form astatine is in, what it reacts with, and where it's moving? By its own radiation. Each astatine atom is its own detector. An organic solvent was added to an aqueous solution. The alpha activity in each layer was measured with a counter. The residue migrated into the organic layer. This means it's in a nonpolar form, like a molecular halogen. It remained in the water. It's an ionic form. An oxidizing agent was added, and the measurements were repeated. A reducing agent was added, and the measurements were repeated. Every conclusion is based not on observation, but on counting the pulses of a Geiger counter. The researcher never sees their substance. They only hear the clicks of the device. A separate problem is radiosity. The residual solvent around it emits its own alpha radiation. An alpha particle flying through water creates thousands of ionized molecules in its wake, radicals, peroxides, atomic hydrogen, hydroxyl radicals. These highly reactive fragments immediately react with everything nearby, including the residue itself and the carrier molecules to which they are being attached. The residue destroys the chemical environment around itself faster than the experiment can be completed. Work must be done quickly at low temperatures in an environment with a minimal volume of solvent. To combat this problem, a Swedish group in Göteborg developed a dry distillation method. An irradiated bismuth is placed in a quartz tube and heated in a flow of inert gas argon or nitrogen to 650 degrees Celsius. At this temperature, bismuth melts, but does not boil, and the residue, which has a significantly lower boiling point, evaporates and is carried by the gas flow into a trap with cold solvent. As a result, the residue ends up in a minimal volume of solvent free of bismuth impurities, an ideal starting point for the synthesis of medicinal drugs. This method has become an international standard. Regarding the physical appearance of the residue, quantum mechanical calculations predict a black or darker purple solid with a metallic luster at room temperature. Its melting point is approximately 302 degrees Celsius, and its boiling point is approximately 337 degrees Celsius. If 1 gm of pure residue 211 were to be synthesized, the heat released would amount to several hundred kilowatts. The substance would instantly evaporate, destroy any container, and create a radioactive cloud. Such a quantity of the residue does not exist anywhere in the universe. But physicists can calculate accurately enough to predict what would happen. We know the electronegativity of the residue, its chemical bonds, its dissociation constants, and its distribution between solvents. We know its electron configuration more precisely than that of many stable elements. No one can see it with their own eyes. It is precisely this energy density, several hundred kilowatts per gram, that unexpectedly turned the residue into one of the most promising tools in modern oncology. The history of radioactive medicine begins with a tragic irony. Our previous video's heroine, Marie Curie, discovered radium's radioactivity in 1898 with her husband Pierre and noticed it immediately. Radium causes skin burns upon contact. The tissue literally dies. Pierre deliberately held a vial of radium on his hand to study the burn. Marie documented the skin lesions on her own palms. Both understood that the destructive power of radiation could be directed against tumor cells. By the early 20th century, in France, Germany, and the United States, people began applying sealed glass tubes of radium directly to skin tumors and seeing results. But ich sehe nicht klug. The tumor shrank sometimes, disappearing. The method was called brachytherapy, from the Greek brachys meaning close. The radiation source is placed close to the tumor, or internally. This was the beginning of an entire medical discipline, but the price was severe. The discoverers themselves were unaware of the long-term effects of radiation. Marie Curie died in 1934 from aplastic anemia, a bone marrow disorder caused by years of radiation exposure. She carried test tubes of radium in the pocket of her lab coat and kept them in a desk drawer, using no protective clothing. Her personal notebooks are still housed in lead containers in the National Library of France. They will remain radioactive for thousands of years. From this tragedy, science learned ionizing. Radiation kills cells. The only question is how to target this attack exclusively at cancer cells, sparing healthy ones. In the 1940s, American scientists developed the first example of targeted radionucleoside therapy. Treatment of thyroid cancer with radioactive iodine-131. The thyroid gland actively absorbs iodine from the blood. It needs it to synthesize the hormones thyroxine and triiodine-131 LARI1. Inject radioactive iodine into the blood, and it will collect in the thyroid gland on its own without any antibodies or carriers. Cancer cells originating from thyroid tissue retain this ability. Radioactive iodine accumulates within them, irradiating them from the inside. This method has been effective for 70 years and is still the standard treatment for differentiated thyroid cancer and hyperthyroidism. However, iodine-131 is a beta emitter. High-energy electrons fly into tissue over a distance of several millimeters. For a large tumor, this is acceptable for single cancer cells scattered throughout the body or micrometastases invisible on scans. This is too crude. A beta particle traveling several millimeters kills not only the cancer cell but also dozens of healthy neighboring cells. The idea of alpha therapy, using alpha emitters instead of beta emitters, arose in the medical community in the 1980s and 1990s. The term targeted alpha therapy gained currency in scientific literature precisely when the fundamental difference between the biological effects of different types of radiation on the cell level became clear. An alpha particle is the nucleus of a helium atom. It contains 2 protons and 2 neutrons. It is 7,300 times heavier than an electron and has a double positive charge. Upon entering biological tissue with an energy of approximately 6 megaelectronvolts, it rips through molecules, knocking electrons from their orbits and creating a continuous ionization trail. The range of living tissue is 40-80 microns, less than the diameter of several cells. All the energy is deposited within this distance. The cell has a DNA repair system capable of repairing or more breaks, but dozens of simultaneous breaks in a single molecule are beyond the capabilities of any reparative system. The cell irreversibly loses the ability to divide. This is important for practical reasons. Cancer is a disease of cell division. Tumor cells that have ceased dividing do not grow, do not form metastases, and gradually die and are eliminated by the body. Killing a cancer cell does not necessarily require tearing it apart. It simply requires depriving it of the ability to reproduce. Furthermore, tumors treated for long periods with chemotherapy or traditional radiation therapy often develop resistance through enhanced DNA repair systems. Mutant cells that can more quickly repair single breaks survive and give rise to drug-resistant clones. These enhanced systems are as helpless as normal ones against the multiple simultaneous breaks caused by alpha particles. Among all alpha emitters, astatine-211 is the most attractive candidate due to its combination of properties. Radium-223 has been clinically used since 2013 under the trade name Exfigo for the treatment of bone metastases from prostate cancer. The body confuses radium with calcium, both alkaline earth metals with similar chemistry, and directs it to bone tissue where metastases occur. For tumors in soft tissue, however, it simply won't reach its target. Actinium-225 has a lifespan of about 10 days, convenient for production and logistics. However, as it decays, it produces a chain of 4 daughter radioactive isotopes. Each of these can break away from the carrier molecule. The recoil from the alpha particle emission is powerful enough to break the chemical bond. The released daughter isotopes migrate throughout the body and accumulate in the kidneys and bone marrow, creating unwanted toxicity. Astatine-211 avoids most of these problems. Its half-life of 712 is sufficient for drug synthesis, delivery to the clinic, and patient administration. The decay pathway is 2-channel and clean. About 42% of the nuclei capture an orbital electron and transform into bismuth-207, emitting X-rays. The distribution of the telepatient's drugs can be monitored with a gamma camera, as in standard nuclear imaging. About 58% emit an alpha particle, transforming into polonium-1, which lives for about half a second, and immediately emits a second alpha particle, transforming into stable lead-207. 2 alpha strikes. No long-lived radioactive products. A third advantage is chemical similarity to iodine. Decades of biomedical chemistry have been developing methods for attaching radioactive iodine to carrier molecules. Many of these methods are adapted for the remainder. How does targeted therapy work with chemists take a monoclonal antibody protein that specifically binds to an antigen on the surface of a specific type of cancer cell. In 1975, Kohler and Milstein developed a method for the industrial production of such antibodies. In 1984, they received the Nobel Prize in Physiology or Medicine. The statoatom linker is attached to the antibody. The carrier antibody locates a cancer cell, attaches to its surface, and the astatine fires an alpha particle point blank. But this poses a serious problem. Its own alpha radiation leaves radicals around it capable of breaking the chemical bond between the astatine and the antibody. The astatine is released directly into the bloodstream and immediately begins to behave like iodine. It accumulates in the thyroid gland, causing unintended damage. To prevent this, special linkers with high radiation resistance, organotin, and organosilicon compounds and nitrodiosinium derivatives, which form more stable bonds with the astatine, are being developed. This is an active area of research that directly impacts the safety of therapy. In Norway, at the University Hospital of Oslo, a research group is exploiting the fact that the astatine is a chemical analog of iodine and naturally accumulates in the thyroid gland. This allows it to be used to treat thyroid cancer using the same logic as iodine-131, but with alpha particles instead of beta. A target of a few cells instead of a few millimeters means significantly less damage to the thyroid gland pair and the laryngeal nerve, which are located in close proximity. At Duke University in North Carolina, phase I trials were conducted against recurrent glioblastoma using the 81C6 antibody using antibody labeled with residue 211. This antibody targets tenosynoac, an extracellular matrix protein that is virtually absent in normal brain tissue but is abundant in glioblastoma. A Swedish group in Gothenburg is working with peritoneal ovarian cancer, a tumor in which malignant cells are scattered in a thin layer across the surface of the abdominal cavity. Synthetic chemotherapy has difficulty reaching them, and surgical removal of each one is impossible. A residue with carrier molecules injected into the peritoneal cavity finds each cell and destroys it. Japanese centers study several types of tumors. Now a little about logistics. Production begins the night before administration or early the same morning. In the cyclotron bunker, physicists load a pure bismuth target. It's bombarded with alpha particles for several hours. The irradiation is complete. The clock is already ticking. The target is intensely radioactive. It is removed by remote manipulators through a lead shield. Heating in inert gas currents, the residue evaporates, is transferred to a trap. The drug is synthesized in protective boxes, quality control, packaging, and courier delivery. All this happens while the substance decomposes right in the container. If 7 hours pass between the time it leaves the cyclotron and the time it is administered to the patient, half of the drug is already converted to bismuth. Hence the strict rule. The cyclotron must be located in the same city as the oncology center. Not in a neighboring region, but in the same metropolitan area, with a transport distance of no more than 1-2 hours. There are hundreds of medical cyclotrons worldwide for producing isotopes for PET scanning, but astatine requires specialized targets, specialized chemical equipment, and specially trained radiochemists. Creating the necessary infrastructure is a decade-long task, and it is the main barrier between laboratory triumph and widespread clinical practice. Now for my favorite part, the one that periodically gets me into trouble in the comments. Not everyone enjoys listening to the same old story over and over again, but without this information, the review wouldn't be complete. So, where do elements come from? Where in the universe does gold come from? Where does uranium come from? Where does astatine itself come from in those moments when it does exist? This question has a specific, measurable answer, and it was only discovered in 2017. The Big Bang, which occurred about 13.8 billion years ago, created hydrogen, helium, and traces of lithium. Nothing else. Everything else in the periodic table, from beryllium to adenosine, was synthesized later in stellar nuclear reactors and catastrophes. Every atom in your body, with the exception of hydrogen, was created in the depths of a star. Elements from cast iron are forged in stellar thermonuclear reactors over millions or billions of years. In the core of a massive star, protons fuse into helium. This is hydrogen fusion, the main source of energy for our sun. When the hydrogen in the center runs out, the star contracts, the temperature in the core rises, and helium is ignited. 3. Helium nuclei fuse into carbon-12. This is gel fusion. Then carbon fusion produces neon and magnesium, then oxygen, neon, and silicon. Each stage burns faster than the previous one. A massive star ends its life with an onion-like structure. At the center is an iron core. Surrounding it are concentric layers of silicon, oxygen, carbon, helium, and hydrogen. At iron, the process essentially stops. The fusion of nuclei lighter than iron releases energy. It is this energy that allows the star to resist gravity. The fusion of nuclei heavier than iron absorbs energy. As soon as an iron core of sufficient mass, about 1.5 solar masses, builds up in the center, the energy source is instantly exhausted in the exhausted. The core collapses in a fraction of a second. Electrons are compressed into protons, and neutrons are ejected in a neutrino stream. The outer layers of the star strike the suddenly stopped core and rebound in a blast wave. This is a supernova. In a few seconds, it releases more energy than the sun does in its entire lifetime. For a long time, astrophysicists believed that all elements heavier than iron are born in supernovae. But when they compared the calculated abundances of heavy elements with those observed in galaxies, a discrepancy emerged. There are more gold, platinum, iridium, and uranium in the universe than supernovae can explain. An additional source was needed, and it turned out to be the merger of neutron stars. A neutron star is what remains of the core of a massive star after a supernova explosion. A sphere about 20 kilometers in diameter, with a mass between 1 and 2 times that of the Sun. Its density is 100 million tons per ton. If a teaspoon of a neutron star were to fall on Earth, it would weigh about 1 billion tons. The matter of a neutron star is almost pure neutrons, packed so tightly that they touch each other. It is the densest matter in the universe that is not a black hole. In binary star systems, where both components have gone supernova, 2 neutron stars remain orbiting a common center of mass. They slowly lose energy to gravitational radiation, waves of space-time itself. Their orbits shrink over billions of years, and the distance between them decreases from thousands of kilometers to mere units. For the last few seconds, they rush toward each other at 1/3 the speed of light. The collision takes milliseconds. At the moment of merger, space-time trembles, emitting gravitational waves. This is a vibration of the very fabric of space-time predicted by Einstein in 1916 as a consequence of general relativity. 100 years elapsed between the prediction and the first observation. To detect such a signal, one must measure a change in distance smaller than the diameter of a proton, on arms several kilometers long. This is precisely what the League, our old friend, can do long, as we mention it often on our channel, the Laser Interferometer Gravitational Wave Observatory. 2 facilities are located in the United States, one in Hanford, Washington, and the other in Livingston, Louisiana. Each has 2 perpendicular arms, 4 kilometers long, positioned at right angles. A laser beam is reflected back and forth along each arm. If a gravitational wave passes through the detector, it compresses one arm and stretches the other. The interference of the laser beams allows this change to be measured with an accuracy of 1,000 thinos of a proton's diameter. So, September 14, 2015, the League detected gravitational waves for the first time from the merger of 2 black holes at a distance of about 1.5 billion light years. The discovery was announced in February 2016. The 2017 Nobel Prize in Physics was awarded to Ralph Weiss, Barry Barish, and Kip Thorne. In August 2017, another event occurred, the GW 170.817 signal. The League and a European VIG detector simultaneously detected gravitational waves from the merger of 2 neutron stars in the galaxy NGC 4993 at a distance of approximately 130 million light years. After 1.7 seconds, the Fermat and Integral satellites detected a gamma-ray burst. Over the following hours, days, and weeks, telescopes around the world monitored the fading glow of the kilonova. Spectral analysis of this afterglow revealed traces of strontium and other heavy elements. For the first time in history, rapid neutron capture, the so-called process, was observed in real time, neither in calculations nor in computer models. in the real universe at a distance of 130 million light years. Astrophysicists estimate that several Earth masses were synthesized in this single event as heavy elements: gold, platinum, uranium, and remnant. Here's how it works. At the moment of merger, several percent of the neutron star's matter is ejected into space. In this cloud of colossal neutron density, nuclei capture neutrons faster than they can undergo beta decay. A nucleus can absorb dozens of neutrons in quick succession, growing to a mass far exceeding any stable isotope. Then, as the neutron flux density drops, the overloaded nuclei begin to shed the excess through beta decay. A neutron transforms into a proton, ejecting an electron. The charge of the nucleus grows. In seconds, a full range of heavy elements is created, including nuclei with 85 protons, including astatine. But the remnant perishes en route. After 7 hours, half of it has become bismuth. After a day, there are negligible traces. After a week, 0. It doesn't survive until the cloud begins to mix with interstellar gas. It wasn't part of the protosolar nebula. It wasn't in the Earth's crust at the birth of the planet, nor during the age of dinosaurs, nor even yesterday. All the gold atoms in your hands have existed since the birth of the Earth. All the iron atoms in your blood, too. The entire primordial remnant was dead long before the first water molecule formed in the cloud, from which the Earth was born. Now let's look at the periodic table. It's a historically significant phenomenon because Ostap's story is written into a larger picture that remains unfinished. After filling the last natural empty spaces in the 1940s, the march into the transuranic region began. Technetium, the first synthetic element, was obtained by Sagre and Carlo Perrier in 1937. It was discovered in France by Marguerite Perret in 1939, a lab technician at the Radium Institute who had been studying the decay of actinium for years. One day noticed an anomalous signal that existed. She spent years of verification before announcing the discovery. She subsequently became the first woman elected to the French Academy of Sciences in 1962. Glenn Seaborg created the uranic elements one after another: neptunium, plutonium, americium, helium, Berkeley, California. In 1997, during Seaborg's lifetime, IUPAC officially approved the name Seaborgium for element 106. Seaborg became the first living person to have a chemical element named after him. The second was Yuri Tselakovich Oganessian. He developed a method for synthesizing superheavy elements using calcium-48 as a projectile. This isotope contains an unusually large number of neutrons, which makes the reaction products more. It was this method that was used to get elements 113 through 118. Oganessian, element 118, was named in his honor in 2016. The half-life of Oganessian is 294, about 2 milliseconds. For history, only a few atoms of this element have been synthesized. The hunt for element 11019 is ongoing. Beacon in Japan, GSI in Darmstadt, and Dubna in Russia. 3 laboratories are leading this race. Technically, this is significantly more difficult than previous syntheses. Heavier projectiles or heavier targets are needed. Theorists predict that somewhere around 126 protons and 184 neutrons, an island of stability should exist. This is a region of the nuclear map where half-lives increase sharply compared to neighboring nuclei. This prediction is based on the Gerhard-Meyer nuclear shell model. The next magic number for protons is after 82. The next magic number for neutrons is after 126. A nucleus with both magic numbers could live for seconds, minutes, years, or even thousands of years. No one knows for. Relativistic effects at 120 protons are so strong that standard periodic may not work at all. Some calculations predict elements that behave like noble gases, although based on their position in the periodic table, they should be metals. Others point to the possibility of chemical bonds not found in any known element. The story of remains is the template for this entire journey. Prediction. Mendeleev pointed to an empty cell. False trails. Wallace and D. Hollyby, Minder, they all saw what wasn't there. Recognition of the wrong approach. Don't look in nature for what nature can't preserve. A new tool, Lawrence's cyclotron. A synthesis. Carson, Mackenzie, and Segre create atoms of element 85. An unexpected application. Oncology clinics in Norway, Sweden, the United States, Japan. 70 years later. For the elements of the island of stability, we are now at the stage of prediction where Mendeleev stood in 1869. The iron atoms in your blood are locked in the core of a star that exploded several billion years before the birth of the sun. The gold atoms in jewelry stores came from the merger of neutron stars. The oxygen atoms you breathe are a product of stellar combustion. Every atom in your body was once part of a dying star. Astatine is the only naturally occurring element that doesn't remember its stellar birth. All the astatine atoms that existed at the moment of Earth's birth perished within the first few days. The atoms of astatine that exist right now were born in uranium ores in the last few hours. Tomorrow they won't be there, but others will be. Astatine is an event. This concludes our journey into the world of the 85th element. Friends, please share your thoughts about this element in the comments. Did you know about it? Was it interesting? By the way, maybe you'd like a separate video about the birth of metals? Opinions vary on this matter. Some write, "Tell me." Others are tired of it. Share your opinion and thank you for being with us. Lately, there's been a proliferation of clone channels that copy not only our covers but even our text. This upsets me, of course, but it doesn't stop me. We'll work on improving the quality of our films to become even better. Next issue, a new table cell. See ya on the Fool's Gold channel.